I am also DNV, as you have maybe understood. We have worked also, class was included in this project about this assurance of simulation models, where we made a recommended practice. I come back to that. So this question, and it's also related to our SEACo project, which we are currently running. There also Stian and Severin and others are involved. So and our our work package 5 is just this testing and verification where I relate to. Right. We have basically two challenges. We have global challenges related to change, so climate, supply chains, increased system complexity, that makes that we need new technologies. We should deliver yesterday, right? And trust may be lacking. And also this digitalization thing which everybody talks about, and it's a global trend, so nobody wants to be left behind, and it also increases complexity again. So all that means that how can we handle that? How can we build trust in our simulations, or overall, really, how can we build trust in the applications? And the answer is very often simulation, as we all agree, I guess. But again, when things get more complex, then this modularization is an answer and a suitable platform. So I talk here for OSP, so I guess we understand that. And then also the need of assurance, because sometimes we will maybe trust on the simulation models a lot, and if it goes wrong, we might be lured into thinking that the reality behaves otherwise than it will do later on, which is, it might be even disaster, or it might cost a lot of money. Both are not acceptable. So modularization is one answer to that. Again, we have seen similar things today. This is actually the system model, one of the use cases of SEACo. You see a vessel in the middle. There are some weather things happening, and we have a crane and a load on it, and we have some power production and propellers, and also a dynamic positioning system. And at least on some level of detail, actually the connections are somewhat like that. Maybe not perfect yet, but that's our first thinking. So by having such a modularization, we can ask the vendor of a DP system to please, before you deliver your electronics, can you also supply this FMU to us? And then we put it in the model, and we experiment with it using FARN or whatever, and get solved a lot of problems before the whole ship is built. And that becomes especially relevant when we introduce new technology, because there we can't know beforehand, but maybe we know the bits and pieces of it. So that's, I mean, that's the basic setting of OSP as it is, as we hopefully know it, many of us. So that is the SEACo use case. And then this trust thing. So we say that if we want to trust in the decision support, this is the end goal, right? We want decision support from the simulation model, but how can that be? Well, only if we can trust the simulation model. And how can that be? Well, we need to trust the components. If that is not there, we have a problem. And therefore we have this RP developed. Actually, when you click on this one on top, you get into the DNV site where this is published. So it's open and everybody can use it as, yeah, not as you wish, as it is stated. So this is clickable, and I have just produced a little bit an overview what is included. As Klaas already said, we see that we have a reality. That's the one we want to model. A model is never the same as reality. We intentionally pick features of that and want to make a model of that. It can never be reality. So how do we do that? Through a conceptual model first. And I will come back to that because while we made this RP, we found that this conceptual model is actually one of the key points here. Verification, validation is something we have heard of, all of us. Maybe we sometimes confuse it, but we have some understanding of what this is about. But conceptual model, that is something we always have in our head. I say that nobody makes a model without a conceptual model. But to make it consciously and to put some quality requirements on top of this conceptual model, that's the point here. So we say that, well, there is some, we do the qualification, risk analysis included. We have something which we call confidence level, maturity level. Can I do this complex model, or should I have somebody who knows better? Checklists, and we check the modeling types and a lot of things here. So again, you can click on that, and I will come back to some details. So that's about the conceptual model and what needs to be done there. Then the model verification class has been a little bit into that. Test methods, verification activities, yeah, things like that. And in the end, when this all is done, we want to do the validation, and that is checking whether what we made is actually what we wanted in the end. So we check against the reality. Does it produce the correct results? So that is basically what is included in this RP, and the appendices ABC. They contain tables of things which can be done and should be done, and where one can pick the things which are needed. So, but when we look here, this looks complex, right? And you see a number of documents here. Well, is that just another thing which produces documentation and is not really worth what we need to do? So another paperwork regime, and it seems contrary to Quick, and it seems true, doesn't it? But what we say is it's not contrary to Quick, it's contrary to Quick and Dirty, and that's an important point. I think that many models and also many software packages, they seemingly are quick, but when you think about the rounds you need to take because you have not done a proper concept, for example, in the end, it turns out it's very expensive. So to have the right speed on things and to arrive more directly to the goal is an important point here. And some efforts which we are thinking about is the better structuring of central activity. So therefore, this conceptual model is very important. Assurance and necessary documentation is a natural part of development process. So I just put this little Python code there because that's for me a symbol. If we could do all this qualification verification work as part of the development, so similar to doing commenting while you code, yeah, then I think it would get much easier. As far as so far, we very often do it in the end when we have partially forgotten things and it's very hard to pick them up again. We forget, we make errors then. I hope we can get to such a thing like that. And we have also started to develop tool support for assurance processes. For example, when you have done your model battery, maybe it's on. You hear me? Okay, good, very good. Yeah, when you have a model description from FMU and we want something which we call design contract, which is a part of the RP, then we translate these to each other automatically. Also these automatic tests like FARN, as Klaus has talked about already. So agile model development is not wrong, and it will take some rounds, but we want to have just the right amount of rounds and do a lot of things while we do the development. That could hopefully help us to get the assurance in place without too much double work or maybe zero double work. So that is our vision here, constructed assurance models in right time, on budget, with right quality, and without unplanned redesign. And we are not there, so we don't say that. But while you hopefully start to use this RP, give us feedback, use the tools, which hopefully at least partially will get open source, and then let's collaboratively get to this point that we make the right models in the right time. I think it's doable, but we need to work for it, and don't accept any type of documentation where you don't feel or where it's hard to argue that it's meaningful. Yeah, I think there's so much documentation which is maybe not meaningful, and we need to discuss that and not only accept, oh, somebody wanted that, so I do it, whether it feels right or not. So now we go a little bit into the SEACo project to have an example. That's the work packages. I made a little bit symbols on top of it, coordinate system transformation, the standardized environmental modeling, obviously important. Coordinate system transformations, we need a lot of these. Tight coupled systems are a problem. I don't have the time, I think, to go into it. The point is, when we have tight coupled systems, the simulation time steps can get very, very small and maybe can't be handled anymore. And also to maybe make them small temporarily, but then speed it up again could be a good idea. And that's things we discuss here, a more accurate and reliable co-simulation so that we get the uncertainty under control when we have a number of components. And then the last one is this assurance thing, testing and verification. So I just pick this crane. You know, I have showed you the top model here, right? The crane gets here. And the crane, it's maybe not hard to understand that it has some of these problems inside. Sorry, say here, right? Because we need to have environmental problems. I come back to that. Maybe I can just go. Oh no, can't. Sorry. Right, coordinate systems we need to transform because the crane has its own coordinate system, but the ship has another one. So we need to translate these to each other, and the crane will tilt when the ship tilts. So we need in some way to handle that. modular tight coupled systems, yes, this the crane is fixed on the boat, but the boat tilting renders tight couplings here. So there is this problem, and how we should handle the uncertainty is also a clear problem here. So the crane here, it includes actually all of these problems. So I have listed some of these here, and we want also to trust it, because when you want to use this crane in the end, for what? Well, you may want to, for example, do operational planning. I want to do this job with the crane. Yesterday, I was visiting the provider of this FMU, and we discussed the case that a heavy lift was done far out, and then the hook broke, and this created actually a big accident. It hit the ship in the end, and then the ship hits the quay where it stood. A lot of damage. Just such a thing, right? And maybe one would want to simulate such a thing, and if the simulation says, okay, that's fine, we can do that, and it doesn't matter, and in the end it happens and it matters a lot, that's not good. So we would like to trust the simulation to get the right results. For example, to find out how far can I go with the crane in some wave heights. That's a concrete question where the simulation hopefully will help and give us good enough answers. Not exact, can't be, but good enough. So yeah, let's move a little bit on. This concept model, I have shown a little bit of what it includes. One wants to do an objective. One wants to define the system boundary of this component model. Requirements need to be defined. How do I want to model that? In the crane case, maybe one use bars and connect them in some way, and then find the position of some things. That could be, so maybe it's just a mechanical model in this case. In other cases, you might have, it's hydrodynamics, and you need to do a lot of things there. Assumptions and limitations need to be listed, and that's a thing which should be done throughout the whole project, and keep this list going and keep it up to date. Risk analysis we want to do because we want to be don't want to be fooled by the model when it's compared to reality. And already at this early stage, it's often necessary to also discuss how do we want to validate that, because finding the data to do so is often time consuming. So that is something which should be discussed as early as that in the project. And that whole thing brings us to this design contract, which is basically an extended model description, including also this type of information. What do you want to use this model for? Because only when you know that, when you have documented that, it's safe to use it in the end. I mean, I can make a model for my coffee machine, but when somebody takes the, look here, it contains a control system, nice, I use it for my nuclear power plant. Obviously, it doesn't work, right? And it's ridiculous, but it happens. Not as bad as that, but still, and we need to avoid that again. Okay, yeah. I think this conceptual model will really help us. Use the time to make it, and then go more directly to the goal of having a good model in the end. So some more details. We had a workshop on the crane where we made colored small pieces. Yeah. Our findings. It's the battery, I guess. right? I switch it when I fails. Brilliant. Works. Maybe you can switch a little bit down. Okay. Yeah. So let's just go a little bit into some of the details as a final thing here. The objective, we went through all the stakers. Who could be interested in such a model? It's both the crane model designer, the ship class could be interested, a vessel designer could be interested because he wants to integrate a crane, and of course the end user, and as you see in this short point list, it's very different things they want to do with this model. Yeah, so and a good model should include all these features, and therefore it's important to identify all the stakeholders first, and then make the model. The boundaries we discussed, so that's just part of the system model I've showed before, identifying a little bit of the connections we have here, and what we now discussed yesterday when we discussed details here. Yes, there is an additional connection between the weather and the crane, because wind forces will also be important directly on the crane structure. So that comes in addition here. But beyond that, I think this gives a good picture of what is important here as connections. Modeling concepts, we have not yet decided that, but it could be Unreal Engine, it could be Modelica, some code there. There is an existing crane example, but it's SEACo. Do we want to use that and extend it? Or would we make just a Python model? It's not decided, but we need to find that out. It will be some mechanical based thing, which because the mechanics are the most important things here. Assumptions, limitations, very important. Here you start the list. And you see, for example, the degrees of freedom will be important. So how is this? How many legs should the crane have? Max, or which exactly? And what we also saw yesterday is obstructions, because actually that again probably makes an additional information necessary, because if we include obstructions, then we need to know how the vessel looks in detail, right? Because then you need to know where is the steering wheel, where is the house here on the ship, stuff like that. Otherwise, it's not there, and then it would just mean to list here obstructions are not included, and that's what we say now in the first version. Later on, maybe we need to include that. So risk assessment, the goal would be to check that we are not fooled in any way. It's not done yet. We found out that we need to do that later when we see more about the model. And availability of data is not simple, at least for the our partners here. So maybe we need to contact oil industry to get data, because they have probably cranes with more sensors installed. Yeah, and here are some of the essential results we want to get in the end, but this is just a list started, and will be increased later on. Right, I think we are here. Yes, thanks. Thank you. Maybe we have time for one question, or the time runs here.
Yeah, I'd say let's do one question and then time runs fast when you're having fun. And farn.
Farn.
It's actually very close to a Norwegian word that always comes to mind when I say farn.
There's one.
So, thanks for the presentation. Firstly, secondly, I would like to ask, what about the the coupling of the movement of the crane, the hydrostatic state of the vessel? Because if you move the crane, it has a load on it.
Yes.
It can change the balance of the ship. So you have.
It will. And that shall be included, at least to my understanding. Yeah. So it would. I mean, fixing the crane on the vessel includes accelerations here in this case, right? Both from the crane to the ship and from the ship to the crane. So these need to go both ways, and that's just the point about these stiff couplings. Really, a very good point on that. So when you get these problems, then the time increment must be not too high, because otherwise you get uncontrollable results, basically. So yeah, that will be an interesting thing to see in the end. Yeah.
Yeah. Also, something about you can use cases I think in the offshore structures area, they use a lot of simulations like that, like cranes on floating devices, etc.
Yeah.
So I think there is a research, a lot of research in this field.
Yeah, I think cranes are focused on a little bit currently. I have seen some other projects too. Yes.
All right, it's getting late. I forgot. Did we say one question, or what did we say now?
Yeah, let's say so. You can ask me. That was my email, and just call me. Finally, I would like to bring out give a hand to both Dion and Serene to have arranged this very nice conference. So I think we learned a lot. Thank you to you both.
Thank you very much. It was a pleasure and honor, it really was. Thanks to all of the speakers and the attendees. Obviously, this wouldn't happen without you guys. It would be pretty boring me just standing here in front of an empty audience. So thank you very much.